welcome to this NPTEL lecture. We are continuing our discussion on reflector antenna system. In the last lecture, we have found the expression for gain of the reflector antenna system, and there we have seen that there is a blockage of the reflected rays by the feed. Also, we have we should point out that not only the blockage, actually the feed also scatters this feed and its accessories. As you can see here, the feed and the accessories, that the reflected rays from this aperture that gets scattered from these. So, that also increases the cross polarization of the fields, because whatever polarization the aperture has given, now that gets disoriented by this reflection. So, sizable cross polarization also takes place. So, for systems where side lobes and cross pole are desired to be 30 dB down, 30 dB or more down, this creates a problem. Actually, 30 dB down is required for many of these satellite communication systems, then radars, etc. So, one solution is to go for an offset feed. Now, you can look at the diagram that this is a offset feed. What is offset? You see that certain portion of this paraboloid reflector contour is cut. So, the feed is not present in the axial zone. The reflector is not present here, and also the feed is tilted. Previously, feed was pointing to this, now feed is tilted. So, here you see that it is such that this ray from this end, this is the maximum that can be reflected. So, this one comes here and this one goes and that comes here. So, that means the reflected ray is only in this zone, and this zone you see the feed is not blocking. So, this is called offset paraboloid reflector. But so that means a circular section of a paraboloid reflector may be cut out such that the focal point lies outside the main beam of the reflector. This improves blocking efficiency, but due to non-symmetry between reflector and field, cross polarization is not improved for this. So, in some radio astronomy applications, the problem is the radiation pattern of the feed, that is generally do not go to 0 at the edges of the reflector. That means, look at here that the feed at the edges of the reflector, they generally do not go to 0, they goes beyond that. Now, so with the reflector pointing towards the sky, the feed is pointing toward the ground. So, it will receive thermal noise from the ground, which reduces sensitivity of the system, and that is crucial for this radio astronomy people, because they do not want this thermal noise. Actually, their signal will be so low, it is almost a noise. There, if this thermal noise comes, then they will not be able to detect it. So, that is why they do not go for this single reflector system as sorry, not single reflector, single feed. So, what they go for, various choices are there, single feed and single reflector, etc. So, their thing is dual reflector antenna system. So, actually this type of feed, which is the classical feed, that is called prime feed or front fed feed. So, the feed is in the front of the reflector. So, another problem is that this, obviously there will be a transmission line to feed these. So, a transmission line from the feed to the transmitter or receiver, because you may be using this for a transmitting system or a receiving system. Now, that will be placed behind the aperture or below the reflector. This necessitates long transmission line, which may give also you significant loss. Now, sometimes the transmitter or receiver that is directly put after this feed, but then the blockage again increases. Also, generally these reflector system are put in the outside. So, putting a transmitter or receiver at the outside creates cooling problem and other problems also. So, that is why this prime feed or this front feed is in the very sophisticated systems they are not used, but you see our home transmission, DTH transmission, this is the standard thing, because our systems are not so sophisticated. We have enough signal available and these losses are taken care of by the thing. That is why you will see that actually when rain comes, then there the suddenly the signal goes. I think in the this football World Cup matches also you have seen that sometimes due to rain the signal is going. So, what they do actually that time they pump more power to overcome that loss, and then after some time you can get it if that is manageable, etc. So, this actually motivates to use for this sophisticated system a dual reflector antenna systems. This will be the topic of this lecture. Here we will do just qualitative way, we will because these things each is a topic on its own and it takes several times to analyze these, several hours. So, we will not do that. So, we have already discussed about blocking of rays by the feed, by the front feed or prime feed. Then we have discussed the thermal noise problem. Then we have discussed about the transmission line loss. Now, we know from our knowledge of coordinate geometry in intermediate classes that reflectors made by rotating an ellipse or hyperbola about their respective axis can form various conic sections. So, ellipse, if it is rotated about its axis, we get ellipsoid. So, ellipse is a two dimensional thing, but if it is rotated we get a section called ellipsoid. Similarly, hyperbola, if it is rotated we get hyperboloid. Already we have seen parabola, if it is rotated we get paraboloid. Now, the importance of this is why we are coming here, because these structures are having two focal points. So, the feed may be placed at one feed point, the second focal point can be made to coincide with the focal point of the paraboloid reflector. This is you see that what I said is that you have for the, let us say, the ellipse, you have two focal points A and B. So, suppose I put the feed here. Now, the rays, this A is such that it is focusing the rays here. Suppose it is a receiving system. So, parallel rays are coming from distance things, then they gets focused at the other focus A. We allow that to proceed, fall on this ellipsoid. So, they will come to feed. Now, by that also, that means I can put it this thing. Similarly, the other thing here, that this is a, suppose the same thing is coming, and here, that means here we, after getting focused, we are allowing it to get again reflected by the ellipsoid. Here it is that thing that it is focused on the other B thing, and it gets reflected and come to feed A. Now, this A is much nearer to paraboloid, this B was much distance from paraboloid. So, these are your choices. Now, these systems are called Gregorian systems. Actually, these are all present in optics. Actually, when lenses were developed, that time one famous optician Gregory, after his name it is a. So, they use ellipsoidal subreflectors. In Gregorian system, so we can summarize that rays from feed gets reflected by the subreflector. So, this one is called subreflector. That means, you see that our this is another subreflector. So, this is the main thing is paraboloid reflector, but this is the subreflector ellipsoid, this is also subreflector ellipsoid. So, in Gregorian system, the rays from feed gets reflected by the subreflector and gets focused at a point. They are allowed to continue and gets reflected from the paraboloid to become parallel. Okay. Now, there is another system which uses the hyperbola, and that is called Cassegrain system. This is called Cassegrain system. There the subreflector is, again Cassegrain was a scientist. So, in his name this thing. In Cassegrain system, show the figure, Cassegrain system, the rays from feed gets reflected by the subreflector. Instead of converging to focus, which was the case in Gregorian, but here instead of converging to focus, they fall on paraboloid and produces parallel ray. So, the rays do not meet at any point here because of the hyperbola's things. Now, the hyperboloid subreflector in Cassegrain system may have its convex face facing paraboloid or concave face facing paraboloid. So, these systems can be analyzed, etc. Also, with this the blockage, we can say the blockage of aperture rays is less in Cassegrain than in Gregorian. Also, the feed and receiver and transmitter can be placed behind the primary reflector. Also, a modest amount of reshaping of the subreflector and the main reflector can be carried out in order to give a more uniform aperture field distribution, hence higher efficiency is obtained. By reshaping the subreflector alone, the desired effect may be obtained. Such reflectors are known as shaped reflectors. In general, for Cassegrain reflectors, feed is in a convenient position, as you can see that feed is here, and actually, so feed you can see that feed is not looking at the sky, the feed can look like the feed is looking at the sky like the paraboloid. So, it is not collecting the noise from the ground. So, feed in a convenient position, reduction of spillover and minor lobe loss. Now, capability for scanning or broadening the beam can be done by moving one of the reflectors. So, this is another thing that you have more play, because where you will put the sub reflector or the paraboloid reflector, since you have two things, your play is more. So, I think there are some offset. No, this is not that. This is an offset Cassegrain dual reflector antenna system. So, you see the feed is not looking at the ground and feed. So, this paraboloid can be shaped. So, now the total ray, they are neither blocked by the hyperboloid nor blocked by this feed. Here feed can be placed behind the reflector also. Actually, you can put it, actually this thing, if you properly shape, this feed even can be put behind the paraboloid reflector. By shaping the sub reflector, aperture amplitude distribution can be controlled independently, and by shaping this paraboloid reflector, aperture phase distribution can be controlled independently. Actually, this is the main thing in a single reflector system. Actually, both the amplitude distribution and the aperture phase distribution we cannot control. Actually, everything gets determined by the power pattern of the feed, but here these two are totally independent. Actually, sub reflector controls the aperture amplitude distribution independently. So, there whatever taper etc. I need to give, that means for side lobe what is to be done, that I can do by playing with the sub reflector, and the main reflector or paraboloid reflector, that actually controls the aperture phase distribution. So, that can be controlled independently. That means the cross pole problem that I can easily tackle by the playing with the paraboloid. So, these two independent things makes it so popular. Actually, Cassegrain systems are more popular compared to the Gregorian systems. So, actually these are from telescopes, these concepts came to microwave antenna, and as I said that optical laws hold good here also. So, they are analyzed the way we have analyzed the paraboloid reflector, same analysis technique can be used here to analyze these systems, and hopefully any of you, those who are interested, you can see that these are, once you know that paraboloid reflector analysis, you can just sit down and see books to do that. It is same technique is used. So, with that we conclude this aperture antenna things, but here we have learnt a new technique, that Fourier transform technique for finding aperture. But one problem I will say that we have seen that some of the aperture antennas can be readily analyzed by this technique. That is, if you know the field distribution over a plane, you can easily find it out. But you see, if you have a curved surface, suppose you have a cylinder on which you have an aperture cut, or a some sphere on which an aperture cut etc., there you cannot put this technique, because there you cannot find the field. Similarly, another thing is, suppose I have a open end as a waveguide top wall, and there I cut a slot. Now, what is the field distribution there? I do not know, because I know the field distribution in the transverse plane, but there on the top wall what will be the field I cannot directly find out from the this thing, but knowing the actual electric field there will be, we will see. So, this method, that what is the aperture field distribution. So, if you know aperture field okay, but always it will not be known. So, we will see a general technique by which you can find out, and that will be based on the technique we have used for wire antennas, that there we have seen that what is the current on the wires. Now, wires, apertures or any antenna, general antenna, there the can we find an current on the antenna. Suppose for apertures, can we find the current? We know the field. Now, are fields and currents related by something? We will see that actually they are related thanks to electromagnetic fields, their propagation and their properties, that we can have some current type of things even for fields, and then by that we will be able to say that if you have any type of antenna, be it an wire antenna or a thing, if I know, suppose partly I know the conduction current through wires, partly I know that aperture from where it is radiating, I know the field, either electric field or magnetic field or something, we can find out some sort of generalized currents, and from that we will make a general method for finding what is the far field radiation. We can find other fields also sometimes, but generally we are interested in the far field. So, at least far field we can always find out. That will be a generalized technique, that will be the theme of our next week's thing. Okay. Thank you.